let's start with two questions. The first question is, if a rigid body is rotating, do you think the angular velocity vector and the angular momentum vector, do they have to be collinear? Can they be a situation where they are not aligned with each other? So that is the first question. The second question is about bicycles. When bicycles are going at a sufficient speed, they can actually balance themselves. You might have seen this in your own experience or seen this in videos. Now the question is, do you think the same thing will happen if the bicycle is going backward? So you can set up an experiment where you have a sufficient length of slope, and then you push the bicycle and let it go going forward and see if it is able to reach the bottom of the slope without falling over. And what do you think will happen if you do it backward? You push the bicycle backward down the slope, and will it be able to do the same thing? Will it be able to balance itself? And you have seen that going forward it can balance itself even if nobody is riding it, if it has a sufficient speed. Right? So these are two questions that today's discussion will help answer. We have already seen last time that angular momentum about the center of gravity of a rigid body is just Ig times omega. Omega is a vector, and we talked about the fact that Ig is a tensor, which is like a matrix. We haven't talked about how it looks like and the details of I. We will talk about that briefly today. And we also talked about sum of moments about the center of gravity is equal to the rate of change of angular momentum about its center of gravity. So these are two concepts we will elaborate on today. Now, before we get into it further, again my usual disclaimer. Remember, these are refresher concept capsules. We just discuss the spirit of the derivations. We don't necessarily do rigorous derivations, so you will have to spend time separately on your own going through these derivations yourself. You will also have to spend a lot of time practicing solving various problems. It's very important to develop that experience on your own. These equations are ridiculously simple, but applying them requires a fair bit of experience, and sometimes it's even an art, how you pick coordinate frames, how you pick points about which you take moments, and so on and so forth. Alright, with that, let's jump into this refresher capsule. Let's talk about moment of inertia for a second now. We are particularly interested in moment of inertia for a rigid body. Moment of inertia is a second order tensor that can be written as a 3 by 3 matrix. Here x, y, z are axes, and the diagonal entries are what we call moments of inertia, and the off diagonal entries are products of inertia. And it so happens that this is a symmetric matrix. Ixy is always equal to Iyx, Izx is always equal to Ixz, and so on and so forth. And it's a positive definite matrix, barring the fact that any one of the dimensions in a rigid body is 0. So it's not an infinitely thin rigid body. This always ends up being positive definite. The other interesting property about moment of inertia is there always exists one set of axes about which this moment of inertia is diagonal, and that axis, that frame is called the principal axis, and about the principal axis the products of inertia become 0, and you always have just a diagonal matrix here. So mathematically you can think of it as saying that this matrix is always diagonalizable. Now this also helps us see that when you are multiplying a matrix times a vector, you can get a vector that is not collinear with the original vector. So you can see right away that the angular momentum and the angular velocity need not be collinear in the general 3-dimensional case. However, that's a mathematical explanation. Now if we were to look at a physical example, let's just make up a very simple example where it's essentially just a point mass, but at the end of a rigid massless link, and let's say this is M, and let's say these are x, y and z axis, and this is point O. Now imagine this is pivoted about O and has an angular velocity omega about z. So essentially what is happening is this point mass will be tracing a circle and this whole rigid massless rod will be tracing a cone. Now in this situation, if you were to find HO and if you were to compare it with the angular velocity of this rigid body, which will only have a component along the z-axis, you will see that HO is not necessarily along the z-axis. I will let you work out the details here. It's a simple enough situation where you don't even need to go through this. You can even directly figure out the instantaneous velocity of this mass. Mass times velocity will be the linear momentum. And then take moment about O of that, and that will also give you the angular momentum. So you can work it out that way as well. Okay. Now let's go back to this equation here. We will use this principal axis and we will now develop Euler's equations for rotating body. But before that, one more remark on this equation. The gyroscopic effect that you hear about a lot and you've seen also perhaps many examples of the gyroscopic effect in effect. That is essentially just this equation. There is no great mystery to the gyroscopic effect. You would have seen a gyroscope. Also, you also get these toy gyroscopes that you can buy and try at home. You will also see videos online where you put this spinning gyroscope at the end of a cone and it doesn't fall as long as it is rotating, right? It has some rotation omega. When you rotate it fast enough and place it freely on this cone, it doesn't fall, it does something else. Right. So it looks very mysterious initially, but if I just draw a side view of this, the angular momentum, if omega is doing this, is really h, is really in this direction, and there is an mg acting downward. So if I take moments about O, okay, this is about g, but we can apply it about O as well. We can apply about g, but then you will have to find the reaction force. So if I take moment about O, it's one step simpler. You can see that you get a moment that is pointing out of the plane of the board, and your current h is pointing in this direction. So then you can work out that your rate of change of angular momentum has to be aligned with your moment vector, which is pointing out. Then that will help you figure out how this thing will move when you need h dot to be pointing out. What will h have to do, right? So there's a little bit of vector working out, but you can see easily that h will have to start moving towards you, will have to start pointing towards you. So that's why it doesn't fall, but it rotates towards you, it precesses towards you. The gyroscopic effect also reminds one of the bicycle balancing problem. Because a lot of people think the reason a bicycle is able to balance itself at sufficient speed is because of the gyroscopic effect, which is not really true. Gyroscopic effect doesn't really have anything to do with self-balancing. And that you will see when you do the backward bicycle example, that at the same speed you should have the same gyroscopic effect, but when the bicycle is going backward, it doesn't seem to help. So there is something more going on. It's really that when you tilt a bicycle a certain way, the handlebar steers itself in the same direction and likewise in the opposite direction. That when you're going at a sufficient speed provides a corrective effect. And without going into too much detail, I can say that that's the primary reason. You can work out the dynamics in a little bit more detail. Okay, now let's talk about Euler's equations of motion for a spinning rigid body, which is essentially this equation. Written for a spinning rigid body, resolved in terms of its principal axis, so that the moment of inertia is now a diagonal matrix. So about the principal axis, we have the moment of inertia matrix. Now let's think of the angular velocity as a vector with 3 components along the same principal axis. We already have the angular momentum equation here, but we need to find its derivative. And its derivative we can think of as having 2 terms. The first term having being due to the change in magnitude of this vector. So let me write it as omega x dot, omega y dot, omega z dot. And the second term, which is due to the change in direction of omega. And since this is a body fixed frame, the rate of change of direction will really be omega itself. So we have seen this before. So this is just Ig times omega. This is the very first thing that we did in the refresher capsule series. Okay, we know what I is and we know what omega is, so we can work out this cross product. And on the left hand side of this equation, we have the moment vector, and let's think of the moment as having 3 components, mx, my, and mz. And let's erase all of this, work out all of this cross product, and just magically write the Euler's equations of motion. So these are the Euler's equations of motion for a rotating rigid body. These are extremely useful and used in a wide variety of applications, including, let's say, spacecraft dynamics. But here today we will use these to study stability of spins. When you have a rotating rigid body and it's spinning about one of its axes, how stable is that spin? To study stability of spins, let's imagine the rigid body is rotating about one of its axes with angular velocity omega. Let's suppose that that axis is the x axis. So our omega x is equal to capital omega. But now let's assume, and the other angular other components are 0. And now let us assume that there is a small perturbation in this and in other components as well. Now the question we are asking is, supposing there are no moments, mx, my, and mz are all 0, and it is initially rotating with a constant angular velocity above angular rate about one of its axes, and there are small perturbations in all 3 axes. How do they evolve with time? Do they grow or do they remain bounded? That is the question we are really answering. Okay, now let us then plug in all of these back into Euler's equations. So left hand side all becomes 0, and right hand side for all the omegas, let's plug these in. So in the first equation we will get Ixx capital omega dot plus delta omega x dot plus minus Iyy minus Izz multiplied by delta omega y delta omega z. This whole thing is equal to 0. This is constant, so derivative of this is 0. These are both small, so product of 2 small things we can neglect. That gives us delta omega x dot is equal to 0, or in other words, delta omega x is equal to constant. So if there is a small perturbation in the same axis about which it is currently rotating, then it doesn't grow, but it remains bounded. It doesn't go to 0, but it remains bounded. The other 2 axes are a little bit more interesting. Again, these are 0, these are negative. So let me bring these to the other side, and I would get Iyy delta omega y dot is equal to Izz minus Ixx capital, let me write, delta omega z multiplied by capital omega plus delta omega x. Here again I can say the product of these 2 small things can be neglected, so I am only left with one product, which is delta omega z multiplied by capital Omega. Likewise, for the last equation, I will again have a very similar equation. Delta omega z dot is equal to Ixx minus Iyy delta omega y multiplied by capital Omega. Now the question is, from these equations, can we say whether the perturbations in x, y and z, do they grow with time or do they remain bounded? So these are two coupled first order differential equations, and you guys know that when you have a first order differential equation, let's take something as simple as this form, then the solution looks like x is equal to some constant c e to the power at, and whether the solution remains bounded or not will depend on the exponent. And if it's a negative number, then it decays with time. And you know that for second order and higher order equations, you can have a complex number here, and when you have a complex number here, you are really looking for the complex number to have a negative real part. That is what you are really looking for. So to apply this idea over here, first let's write this in matrix form. So once we write this in matrix form, we then have to use this idea that here it was just the coefficient that was really appearing in the exponent, but when you have a matrix equation like this, it so happens that the exponentials have the eigenvalues of this matrix. So now we have to find the eigenvalues of this matrix. So let's think of this whole term as A and this whole term as B. So we are essentially finding the eigenvalues of a matrix that looks like this, and using this idea, if those eigenvalues have negative real part, or rather don't have positive real part, then they don't grow and they remain bounded. If they are complex, if they are real, then both of them will have to be negative for your perturbations to not grow with time. So to find the eigenvalues of a matrix that looks like this, we really have to solve this determinant equals 0, right? So you get lambda squared minus AB equals 0, or lambda is equal to plus or minus square root of AB, and we can plug in values of A and B over there. We will get plus or minus square root of, I get IZZ minus IXX multiplied by IXX minus IYY divided by IYY and IZZ, and I have two omegas here. So I have this whole thing multiplied by omega squared. So this leads to a very interesting insight, because as we were just talking about, if lambda, one of the eigenvalues, happens to be a positive number, then you will get the perturbations growing. But if the entire thing inside the square root sign ends up being negative, then you will have purely imaginary poles, imaginary eigenvalues rather, and in which case you will have bounded response. So the whole thing depends on the sign of this term, IZZ minus IXX multiplied by IXX minus IYY, because omega squared is always positive and the other two terms are always positive. So let's examine this term. So let us examine 4 different cases. So case 1, let's say IYY is greater than IXX is greater than IZZ, and let's say case 2, is the flipped version of this. IZZ is greater than IXX is greater than IYY. And of course, I am conveniently omitting equal to here just for simplicity of discussion. So, in the first case, both of these terms end up being negative. In the second case, both of these terms end up being positive because IXX is greater than IYY, so this is positive, IZZ is greater than X. So, let me use the same color. Which means that the entire term within the square root sign is positive in both these cases, which means when you take the square root sign, you get a plus or minus real number, and that puts us in trouble because when you have a positive real number here as one of the eigenvalues, then your exponential that we were talking about here earlier, your exponential will grow with time, which really implies that when you have a perturbation of delta omega y and delta omega z, those grow with time. Now, let us look at two other cases. Let us go back there. Case 3, let us say IXX is greater than both IYY, IZZ, and case 4, let us say IXX is less than both IYY and IZZ. Here you will see that in both cases, the product is now negative. So, let us look at case 3. So, IXX is greater than IYY, IZZ. So, this term is positive in case 3, whereas this term will be negative. And case 4, it is the opposite. You will see this term is positive because it is less, whereas this term is negative. So, in both these cases, the product ends up being negative because it is a product of a positive and negative number, and the whole term inside the square root sign ends up being negative, which means you will get plus or minus imaginary poles, imaginary eigenvalues rather. And what that means is your solution will look like exponents of imaginary numbers multiplied by time, and you know that that essentially looks like sines and cosines, sine terms and cosine terms. So, there will be some oscillations, but it will not grow with time, it remains bounded. So, the key insight here, which is a very interesting insight, is that if the original axis about which the rigid body is spinning, remember we started with the assumption that capital omega is the spin rate about the x axis. If that happens to be the axis of intermediate inertia, then it is unstable, the spin is unstable. Whereas, if that happens to be the axis of the highest moment of inertia or the lowest moment of inertia, then the spin, the perturbations remain bounded and they do not grow with time. So, it is always much more stable to rotate about highest moment of inertia axis or lowest moment of inertia axis. So, that reminds me of an interesting example. Many of you might have seen the movie Interstellar, and I think that is a very interesting movie even from the point of view of dynamics, because you see a lot of interesting things there. But you see this in action. If you remember the scene where scene in which Dr. Mann tries to dock onto Endeavour, the space shuttle, and something goes wrong and there is an explosion and Endeavour is spinning, and these other guys try to go and we engage with Endeavour while it is spinning. So, you could ask this question: when there is an explosion like that, the spaceship is already spinning, is this a stable spin? Will it continue to spin in the same way, or it will start to wobble and start to spin in various different directions? So, Go back and look at the scene and see if what we just talked about here makes sense there. So these insights here, again let me repeat, the insight is that when you have a spinning rigid body, spin about one of its axis. If that axis happen to be axis of intermediate inertia, not stable, whereas if the axis happen to be the axis of highest moment of inertia or lowest moment of inertia, then it is stable. This you will see everywhere. And in fact, the tennis racket theorem, if you go back and look at tennis racket theorem and see if this provides you an explanation for the tennis racket theorem, you'll be able to connect this. You'll be able to connect this to that. Okay, so with that we end this capsule, and remember, you can learn anything on your own, even if you have very modest resources. Everything is available online. All you need is a little bit of patience and commitment.